Statistics and probability, the parameter estimation. Parameter estimation, a branch of statistics that involves using sample data to estimate the parameters of a distribution. It also refers to the process of using sample data, like in reliability engineering, usually times to failure or success data, to estimate the parameters of the selected distribution. Types of parameter estimation. For each population parameter, there are two types of estimates: point estimates and confidence interval estimates, or the CI estimates. The point estimate from a sample is computed first for both continuous, like population mean, and dichotomous variables, or population proportion. For both continuous and dichotomous variables, the confidence interval estimate is a range of likely values for the population parameter based on the point estimate, like the sample mean, the desired degree of assurance for the investigator, most commonly 95%, but any level between 0 to 100% can be selected, and the point estimates standard error or sampling variability. The examples: let's say we want to calculate a 95% confidence interval for an unknown population mean. This means that the confidence interval has a 95% chance of containing the true population mean. As a result, P, sample mean, margin of error plus margin of error is equal to 0.95. The central limit theorem introduced in the module of probabilities stated that for large samples, the distribution of the sample means is approximately normally distributed with a mean in that sample, and the standard deviation, also called standard error, P, which is negative 1.96, Z 1.96 is equal to 0.95 for the standard normal distribution, which means that a standard normal variable Z would fall between negative 1.96 and 1.96 with a 95% likelihood. For large samples, the central limit theorem says this formula. By substituting the expression on the right side of the equation is this formula. We may use algebra to rebalance the inequality so that the mean is the middle word, as seen below. The 95% confidence interval for the population mean is given by this last term, which can also be written as this formula, where Z is the value for the chosen confidence level from the regular normal distribution. For example, Z is equal to 1.96 for 95% confidence level. In fact, we sometimes have no idea what the population standard deviation is. The sample standard deviations can, however, be used to approximate the population standard deviation if the sample size is high and greater than 30. Is the methods of parameter estimation. Estimators are the tools that are used to estimate parameters. Some estimators are probability plotting, a process for determining parameter values that involves plotting data on special plotting paper and deriving parameters from the visual plot. Next, rank progression, the least squares. The sum of the squares of the residuals is estimated using this method of finding parameter values. Third is maximum likelihood estimation, a method for determining parameter values that maximize the probability function given a collection of observations. The next is Bayesian estimation methods, a set of estimation methods aimed at lowering the posterior expectation of the utility function. In practice, this means formulating existing knowledge about the situation, gathering data, and then using posterior knowledge to update our beliefs. Qualities of estimators. We say an estimator is consistent if the value it estimates for a parameter theta always converges to the real parameter value as the amount of data used for the parameter estimation grows. An estimator's bias is the difference between the expected and real true value. When the bias for a given estimator is 0, we assume the estimator is unbiased. The variance is a third statistic that informs us about an estimator's reliability. We assume an estimator is more effective if it has a lower variance than another, and we can measure the efficiency of estimator P relative to estimator Q as variance. About parameter estimates, also called sample statistics, parameters are descriptive measurements of a population as a whole. However, since it is impossible to quantify an entire population, their values are normally unknown. As a result, you can estimate parameter values using a random sample of the population. There are few different kinds of parameter estimations. A parameter's single most probable value is called a point estimate, the sample mean. For example, is the point estimate of the population mean the parameter estimate. Confidence intervals are a range of values likely to contain the population parameter. Consider the following scenario. You work for a spark plug manufacturer who is investigating an issue with their spark plug gap. It would be prohibitively expensive to measure each and every spark plug made. Instead, you pick 100 spark plugs at random and weigh the difference in millimeters. The sample's average is 9.2. This is the population means point estimate. In addition, you build a 95% confidence interval for which is 8.8 and 9.6. This indicates that the true value of the average distance for all spark plugs is between 8.8 and 9.6.